corrosion.
behind.
I mean, if something is gone,
Yeah,
what happens?
I should try it. But it should.
You would like to answer, you should have been tried.
Yeah. But it should work, but it's dependent on the size of the crack. If it is bigger than this crack, I mean, I'm not sure it can work by using this until the 2 corrosion inhibitors. Yeah. So therefore, maybe 4 or 5 corrosion inhibitors with different solubility, maybe it can work. But it should be healed. It can be worked. I mean, why I used big size of effect in order to see if it is working for big size or there is more than one small scratches to cover or not. So it is 600 times more than usually what used in self-healing.
And the accessibility to cracking in the surrounding, in the vicinity, how is it? Is it more sensitive to cracking? Or
No. It is silica film. Here it is silica film. And there is no defect in the film structure. So therefore, the same as here. It should be more the same as here.
Next question.
Okay. Maybe we can start with the picture number 12. Can you go to that? Yes. So we already discussed a little bit earlier silicate. And so that's the reason why I come once more to this topic, because you have written here on the left side very much our metal alloy. And then the cross-linked silicate film. So if you go back some minutes, what would be really a silicate film in this picture? And only the silicate film. Yeah, on the left side.
Silica film.
Yes, because you have written cross-linked silicate film.
Okay. Actually, in the literature, there is CLM film, soldier film, and there is really.
No, we are not talking about soldier film, we are talking about silicate film.
That's silica film.
Yes, only the silicate film. So just look at the picture, you can give me the answer. It's a very, very simple answer. You have the laser pointer just cooked.
Where is silica film?
Yes, where
This is all silica film.
no, that's not all. It's a specific point where I really would like to say, that's the silicate film per definition, what silicate means. As we have defined earlier this way.
As a here, this is.
That's not a silicate film.
Usually there is aluminum oxide.
That's a silicate film because here you have Si, let us say in general, Six O by minus. Yeah? And that's a silicate film. The rest is only an SiO, SiO. Yeah? And that's, let me say, carefully, like whatever. So it's like a little silicate. But the silicate film only is, if you are talking about that, only if you're talking about okay, it's a minus. Okay, so could you go to, I really like that picture. I think it was 20, 21, 22 around that. Let's go back to the question of Professor Duncan. Oh, it's not one is more, which one is that? One more? Oh, one is it more? Oh, it's 21. 21? No, 21 is fine. So, that was, selfie. You use, as you said, urine oxide, it's generation of urine oxide. That's okay, I understand this. I really do not understand the benzotriazole. What is benzotriazole doing? I think you have shown me the formula page 1 or something like this. Also, what is the reason for using benzotriazole?
Is a energy inhibitor.
So just do this one, yes. It's a complicated formula. Okay? So what is it doing in this healing process?
So it has a positive charge.
I Okay. So that benzo fire zone is just sitting somewhere in between the silicate and the side. Okay. Say how many months more next to the
There's a formation of the silicon side and it has the effect and so therefore I use basically also just to cover the failures in the silicon oxide layer to obtain better
using both.
Because the potential is better than it was before.
So let us go back to this beautiful picture and let us go back once more to nanoparticles. Because as you said, you used silicon oxide, what was it? Sodium oxide and silicon carbide, I guess. And also you have shown us how carefully said how you can prepare the appropriate nanoparticles, as in the case of silicon oxide. This is a dual process. So the size was 50 nanometers. You said, how can you control the formation of a 15 nanometer size, that is a nanoparticle? Which method are you using?
Yeah, I made an SCM by 200 nanometer size. This can be microscope or this film with nanoparticles. Yeah, and the size it is not mentioned here. It is about 200 nanometer size.
Is that a nanoparticle? Now we are going to use a definition of nanoparticles. What's the definition of nanoparticle?
It's a particle with a nano size.
Okay.
It is a particle in a nano size.
So your size is 999 nanometer is a nanoparticle. And 0 point, it is 0.1 nanometer is also a nanoparticle.
No.
No. Okay.
It can be micro, no.
Then you say nanometer size. It goes from 0.00001 nanometer to 9990.99999. Or even to 5,000 nanometer. I don't know. Is that a nanoparticle?
No, it's not nano.
So what's the definition for nanoparticle?
Less than
Or more than? Exactly.
yeah.
That's a sharp definition.
Let's say 500 nanometer or
Wow, too much. It's 5 to 100. That's the definition. But let me come back. You said you use, I don't know, is in discussion, 50 nanometer. Well, let me say 200 nanometer, but then never talk about nanoparticles. How can you exactly get, let me say, it doesn't matter, define the size of particles. How can you control it?
sorry, I try, there is always a agglomeration of the particles,
Of course.
but I try to avoid it by ultrasonic.
So it's
To avoid the agglomeration.
yeah.
And the size is between 50 and 100 nanometer, 150 nanometer, the size of the particles.
As you have two possibilities. How can you generate and stabilize nanoparticles? Which was the generate? The possibility of nanoparticles. That's a naturally interesting.
Can we stabilize the particles?
How can you generate? In generate and stabilize nanoparticles? There's a boost or doesn't matter. There are two possibilities. It's a top-down or bottom-up process.
What I need here is the OPH value, so that's when there is a repulsion between the positive charge and so therefore
That's one possibility to use the calculation.
OPH or like pH value.
For example, we're also using the polymers like polyamide, polyethylene glycols or something like this. So also you can really access to the there are two possibilities in one part and the top-down process. But let me come back once more to this beautiful picture. Because I understood that you do approach perfection, of course. That's great. And now we do have in this blue part, or the next one, because that you see clearly. So we do have now for sulfur here, we have other particles in, we have events of triazoline, etc. We have beautiful layers, but you also have what is called intervals. And you're using this design tool here at ambient temperature most probably. You're not interested in using that at 200 degrees Celsius or something like this. Is that right? Yeah, if you said the question, what's the temperature? Is the temperature playing a role here for later on because of applications or something like this?
For the self-healing, yeah.
No. Later on you have a beautiful soft surface, it's a perfect surface, a perfected surface, etc. No, like a motion. What would go on if you have now here an epithelium oxide, or just nanoparticles, like silicon, what was it, carbide oxide, or zirconium oxide, and you are heating a little bit this fluid, let us say to 100 degrees Celsius. 8,000 right? Because you shouldn't ask me a question, but it doesn't matter. I don't
Because
you have nanoparticles, okay? You mentioned that. And nanoparticles are showing different properties than epithelial particles or layers. One reason is, or one property is, that if you are just looking at metal nanoparticles, you can clearly lower the temperature, or other way around, you have a very high, as already discussed, reactivity. Much higher reactivity. And so I would suggest, if you are warming up those tools, nanoparticle passes a critical point in this thing, because what could you form at the interface of your silicate, siloxene, or your aluminum magnesium interface? If you have oxide or carbon nanoparticles.
But how much one to do?
Oh, that doesn't matter. You can take, it doesn't matter. Let me say we take 7 nanometer particles, it doesn't matter.
Actually, when I use lithium carbide as a cause of fire, there is no difference in behavior.
But secondly, we mentioned that if you have silicon carbide, silicon oxide, if you have zirconium oxide, and the rest, so you can get what? You can get formations of, I don't know, even in the presence of benzyl tyrosol, you can have formation of metal carbide, metal oxide, metal nitride, maybe tolerant, I don't know, some other materials, I don't know. So that would be an interesting question looking into this interface of because you never compare the behavior as a property to other properties is stability. Did you use or did you find something?
But I didn't like different way because I can check if there is a layer or different in the structure. I didn't find it.
Okay, thanks a lot.
Even when it is always in low concentration, 1 gram per liter or 2 grams per liter. It's not high concentration.
Die Fragerunde ist jetzt für das Auditorium, also für Sie eröffnet, und wenn Ihnen Fragen sowohl auf Deutsch als auch auf Englisch. Ich darf Sie bitten, ruhig aktiv zu werden. Ich hätte auch noch die eine oder andere Frage.
Sorry, did you use the particles just only as the purpose of healing the cracks, or also did you study mechanical stability or mechanical properties of such coatings, or just as the corrosion studies, you use these particles?
Also the particles are used to reduce the cracks and remove the film thickness, not for self-healing. But I didn't study the effect of nanoparticles on mechanical properties. Because in order to improve mechanical properties, I should use cross-linking agents, which can improve the structure, I mean the hardness of the structure. But the problem is it will reduce the stability of the solvent. Therefore, I'm trying to find something different from cross-linking agents. But the nanoparticles are added to improve the film thickness and crack frequency. Of course, there is much better hardness or scratch resistance in the case of nanoparticles, but still cannot be compared to, for example, anodizing of aluminum.
Thank you.
you possibly have answered this, but I didn't understand. This nanoparticles are improving the film thickness. At the same time, they are improving the, restricting crack. So to me, it seems like the film thickness increases because you have nanoparticles and high surface area and reaction is more, polycondensation. But at the same time, if polycondensation is more, it will generate more shrinkage and more water and all such, which can lead to cracking, more cracking.
So the cracks is not only from water, there is polycondensation will be less because the nanoparticles in this area will form. For example, if I have 100 molecule here, here will be less than 100 molecule in this area. So therefore, cross-linking will be less.
No, but if you have a nanoparticle, the surface area, volume by surface area ratio will be high. So the reaction will be much.
But there is no reaction with silicon dioxide. I'm not sure there is a reaction between SROH and the nanoparticle. No?
Die Kollegin in der vorletzten Reihe.
Well, I have one question regarding particles and penetration. So I know you did that. We saw that you anodized magnesium and aluminum, plasma-like and normal, classical. So, and then I know there's one picture, not seen over here, that you really fill the pores of the anodized aluminum. Yeah, and that is a kind of barrier what you have mentioned. Now back to the particles. If the particles are in diameter thicker, bigger than the pores, and the pores are, well, the pores of the anodized surfaces are around 50, or okay, less than 50 nanometers. So where are the particles gone?
The ceiling of anodized aluminum without nanoparticles, because I don't need
Okay.
But in the case of plasma magnesium, analyzing by plasma, porous 100 micrometer, so I need the nanoparticles to avoid the cracks in the silica film.
And in the rigor also we have been talking about the structure of the PEO anodized surface. And let us get rid of the upper layer, the very brittle layer. Then we see more or less dense there. But you told us, explain, there is still some kind of cracking. Are these cracks really filled? Did you check that? Are they really filled with your soul and form a stable gel, including the particles? I really don't know. I did not ask you that before. What's happening in the upper part of the
There is a
picture?
Here is
Right.
Here is silica diamond.
Okay. And it penetrates the barrier, so it penetrates in the upper.
It's penetrating the porous also and to fill the cracks and defects.
Okay.
So therefore, the upper surface, the surface of the sample looks like.
Okay, that's fine. But please go back. So we know that once in a while the upper layer is going to be removed. Yeah.
Yeah.
Do we have any penetration of the lower layer? I mean, that would be interesting.
Why did the upper layer remove? Because here is silicate film formed over the surface of the substrate.
Yes, Mr. Darvish, we know that this is the case in your specific experiment, but some people get rid of that to have a nice surface. And then the question is, is your soul able to penetrate the cracks or the imperfections which are still in the lower layer? Did you check that?
No, I didn't check because I didn't remove the outer layer. But it will be not less. It will be not less than the thickness, the diameter of anodized aluminum. So therefore, it will be filled.
Otherwise, you would not find all that effects will have been done.
Quick question, if you could go back to slide 24, please. Exactly. axis of that plot, I find that the y-axis is actually a logarithmic scale plot. Why do you choose that scaling?
The difference would be here between the pairs.
Okay, so if I'm trying to be a bad guy here, what I see is that actually for very short immersion periods, self-healing is quite efficient. But then obviously after relatively short times it's not. So if you were to put that on a conventional scale, it would basically look like a very steep drop and then nothing. Right? I mean, this is another reason why you probably put it like this.
The period here is a corrosion, there is a high corrosion, because up to now, after about 100 hours, I haven't self-healing layer under effect. During this time, there is cerium oxide and as well leach out of the field to form a layer. And the effect of the layer can be seen here now, in this area, between 100 hours and 700 hours.
This is excellent because you've basically answered the question that I was going to ask. So thank you very much. I was going to ask why that shape. So, any additional questions, weitere Fragen aus der Auditorin? Wenn das spontan nicht der Fall ist, dann wissen die meisten von Ihnen, wie es jetzt weitergeht. Ich darf Sie bitten, zusammen mit den Kandidaten einen Moment zu warten. Die Prüfungskommission wird sich jetzt aus dem Raum begeben. Ich darf auch die aktiven Kollegen aus der Fakultät für Maschinenbau dazu bitten. Und wir werden uns also nochmal kurz schließen und danach kommen wir wieder rein und werden dann zunächst Sie informieren, also wir holen Sie raus und danach kommen wir wieder rein und es wird wahrscheinlich recht schön.